I would like to go over some of the features from PyMOL covered in the video tutorial. Let's start by examining the beta sheet file that I've provided for you. Open the beta sheet, and by clicking, I can drag and turn this around. Let's first change my mouse because I'm actually only using a trackpad. I'm going to switch to one-button viewing mode. However, it's highly recommended that you use a mouse with this. It makes everything a little bit easier. I'm on a Mac, and right now I can press Control and move up and down on my trackpad, and I can zoom. Clicking Option as I do this allows me to recenter, and I can just turn this around in general by clicking on it. I'm going to recenter this just a little bit. First of all, I want to go to Display and turn on the sequence. You'll see the amino acid sequence shows up here, and I can select things from the sequence itself, and I can select residues by clicking on them in the structure. Let's look at different ways to display this structure. Under Show, I'm going to show the beta sheet as a cartoon. Now it's just showing me the way that the beta sheet is aligned, and it's put in these little arrows to show me the direction of the amino acid chain. I did the Show As command, which will change the view of this. However, if I show as a cartoon, then go back to Show and add on lines, I can look at the amino acid residues overlaid with a representation of the structure in 3D. Now right now it might be pretty straightforward to look at all these amino acid residues in the short sequence I have. However, when we're viewing full proteins, the cartoon view is very nice for viewing overall tertiary structural features. Note that this is the primary structure up here, and this is showing the one-letter codes for the amino acid in the sequence. We can change the display of the sequence mode, and if you don't know your residue codes yet, which you should memorize, you'll need to know them for many classes, you can display as residues, and now you can see this is expanded out and we have the 3-letter codes for the amino acid residues. And I'm just going to go back to the code view for now. In this tutorial, you will look at an alpha helix, a beta sheet, and you're going to show some of the hydrogen bonds that stabilize them. I'm going to change my view just a little. I'm going to show as the cartoon, and I'm also going to show as sticks. In this, as long as you color everything by element, and I always encourage, if you'd like it a different color, please color by element, because your oxygen atoms will always be red, your sulfurs will always be yellow, and your nitrogens will always be blue. And so that's kind of a nice thing to view. I'm going to change this. Pink was not contrasting enough against the red, so I want to just change this view a little bit. So we can see how these beta sheets are aligned, and I'm actually going to control and drag to kind of get a better view. Now, let's try to measure. So with this displayed, let's go to the wizard, and we'll go to the measurement wizard. Now, the beta sheet is stabilized by hydrogen bonding interactions between these anti-parallel sheets. And so let's try to show some of these. The NH of this amino acid is likely hydrogen bonded to this carbonyl. And so I can click here, and I see a measurement appear, and this shows me that these are in range of a hydrogen bond. Now remember, for your tutorial, I would like you to use a white background. So before you do any of this, you might like to change it to a white background so you can pick a color of your amino acids that contrast well. When you're done with the measurement wizard, you can simply click Done. And these measurements, they can actually, since we changed this and it's hard to see this measurement, we can actually change the color of individual measurements because everything will show up here will show as a different object. Now we're going to go into a little bit more of an advanced consideration. We are going to search the protein database, www.pdb.org. Here I know the author of a paper that I'm looking for. This is the final part of your tutorial. And so I want to write in Tim, and let's go ahead and just put MUP1 for the mouse urinary protein 1. Some files will show up, and so here's the mouse urinary protein. I see the authors are the authors that were listed for the article, but this one is just the unbound or apoform. This one is bound to hydroxymethylheptanone, and this final one is complex with sec-butylthiazolene, which is the structure that we're looking for. I'll click on this, and I can download files, and you download this PDB text file. And so I can just drag this to my desktop. And now, if I want to look at this, I can look at it in two ways. I can go to text edit and see the code. Now, what the crystallographer enters in here is basically, let's get down to the sequence. So they enter these in, each atom at a time, what atom it is, and coordinates in 3D space. So these text files are actually modifiable, and you can change them if you want for your protein. However, we're going to just view this in PyMOL. So when this comes up, it's displayed as lines, and it's very busy. We can already start to see that a protein is a little more complex to view. We're going to show this as a cartoon, and we can now see this beta barrel structure that they talk about. Right now we're kind of looking down the center, and this is the binding pocket where the ligands will bind. This is an alpha helix right here, and there are these short helices called 310 helices. The beta barrel is just made up of beta sheets, and you actually did see these when you did your alpha helix section and your beta sheet section of the tutorial, because I simply cut these sections out of MUP for you to look at hydrogen bonding. We're going to go ahead and change our mouse to one-button viewing because I don't have my mouse with me today. And we're going to display and put our sequence on. Notice that this starts at residue 19, and it extends all the way to, this is 171, so 2, 3, 4, so 174 residues. These CDs, these are cadmium ions, and these result as part of the crystallization process. This TZL is the ligand. And you can know this if you're viewing in the one-letter codes, which I highly recommend. You'll see little breaks for things that are not actually physically bound together in a covalent bond. So this is our ligand. We'll get back to that in a moment. These O's, these are all the water molecules that have crystallized with this structure. Crystal structures are actually very wet protein crystal structures. A small organic molecule might crystallize without solvent, but these have to be crystallized with some water molecules associated with them, or they'll lose their biological shape if they dry out. So these O's are all of the waters. Remember, we can't see hydrogen atoms. The reason for this is crystallography is actually done by bombarding the crystal of a protein with X-rays. X-rays bounce off the electrons, and we generate this model. However, with hydrogen, it only has one electron, and it cannot be seen by crystallography. Now, let's go ahead and do some commands from your tutorial. What I'd like to do is define my active site. In the command bar, we will type the residues of our active site. Note that all of these have shown up as a selection, and the selection has been called active. By putting select active, we're defining a selection so it shows up separately. Now I want to show sticks, and it's very important that I don't do show as sticks. If I do show as, it'll chop out, notice how it chopped out some of the cartoon of the protein. I can fix that easily by showing the cartoon of the protein, but just make sure you're not chopping anything out when you're selecting your active site. I'm going to go ahead and zoom in a little bit more to look at this active site. Now, if I'm getting a little confused because everything is green, I can recolor my active site, and I can do this by element, and I'm just going to make it a little bit of a different green so it's easier to see, and now I can see where this is protruding out of the backbone. Now I'm going to define the water molecules that are present in the active site. MUP has this important hydrogen bond network. So what I am saying is I know that residues 56, 58, and 138 all have water molecules near them. So I will do this, and now I can see the two water molecules that are associated with my hydrogen bonding network. I can show the spheres for my active water with a typed command, or I can do it right here. And I can show as spheres. Now these are very large. You can see that they're really filling up space, and they're not the actual size of water molecules. If the van der Waals radii was really this big, these would be repelling each other. We're going to use a command to make these a more reasonable size. Our command for this is alter active water, and here we're setting the size of the van der Waals radius. Now, this doesn't do it right away. You have to type rebuild, and that will resize the water molecules finally. Now, let's go ahead and show our thiazolene ligand. And so I'm going to go move to the code, find our thiazolene, and this is going to be my selection now. I want to show my selection as sticks. And I'm going to color it differently because I really want to highlight this ligand. So let's go ahead with kind of a yellow color. You can see that pretty well. And so this is still colored by element, so I can see my sulfur here and my nitrogen of my thiazolene here. And now I want to show how this interacts with my hydrogen bond network. But what I'm going to do first, if I start selecting other things, they'll add to this selection. So what I'm going to do in my actions is rename my selection. Now when we defined the active site by typing in here, it showed up as its own selection. However, we can just select things from the code and rename them to define them as their own selection. And I'll call this one ligand. Now I want to use the measurement wizard to show the interactions of my thiazolene ligand with these water molecules. So I'm going to zoom just even a little bit further in so I can see things better. And this nitrogen atom is actually hydrogen bonded to this water. Enter the measurement wizard. I will click on my first atom and the second atom, and we can see that this is nicely within hydrogen bond range. We can display the hydrogen bond between the two water molecules and any other relevant hydrogen bonds in this network. But I'll leave that up to you as you work through your tutorial. Thanks for watching.